let's continue. Okay, so before the break, we looked at how the loss can be decomposed into three components, right? Like bias, variance, and the inherent noise in the process, right? So let's actually look at a practical example so that we understand the three components better. Okay, so we're going to do regression now to compute the true risk, bias, variance, all these things. We need access to the joint distribution, right? So what I'm going to do is like I'm going to do the synthetic example that we did, where we can actually define the distribution. Okay, I'm going to do the regression with the sine 2 pi x example that we did before, right? Now I'm going to take the sine curve data generation process. I'm going to generate 100 different data sets, each with 25 examples. Is that clear? So I'm generating 100 different data sets, each with 25 examples. And the model I'm going to use is a linear regression model with Gaussian basis function. Okay, let's say we have 24 Gaussian basis functions used as the features. Okay, so I'm going to do linear regression with L2 regularization. Okay, and this is like here you see for different values of lambda, right? Like what is the effect, right? So in the top, you see the situation when lambda is large. So when lambda is large, it means I'm highly regularizing the model, right? So when you regularize the model too much, it's getting closer to being a linear model. So the bias is very high. The variance is low, okay? Why do I say that? You can look at the figure. So for different data sets, for 100 different data sets, the red color lines are the different solutions I got by training on these data sets, okay? So with 100 data sets, I got 100 lines or 100 functions, okay, they're not lines. So you see that they all are very close to each other. So the variance is low, but the bias is high. Why is the bias high? Because the average red line looks very different from the true green line, right? So this is an example for high bias, low variance. Okay, now look at the bottom. When lambda is too small, right? So when lambda is too small, the variance is high. What does this mean? Like this model is going to overfit, right? Like so, you see that if you just look at individual curves here, they all look wiggly. Okay. However, when you take an average of all these 100 complex curves, you get a curve that is actually very close to the green. So which means when you have more complex models, the bias is low, the variance is high. Okay. So when you have something in between, you see that you're approximating okay, and like the variance is also okay. Is that clear? This is like a practical example of how the bias variance trade-off works. So when you have a very complex model, which means regularization is low, then bias is low, variance is high. When you have a highly regularized model, then the bias is high and variance is low. Yeah.
You said that the bot is okay.
The individual models might be overfitting. They might be overfitting. Okay, so now we can also compute the bias, the exact bias, the exact variance, the exact true risk. Okay, why? Because we have access to the true distribution, right? So the average prediction, let's just call it h bar of x, is given by 1 over L summation L is equal to 1 to capital L H L of X. Okay, because L is actually the number of data sets. Okay, so L is the number of data sets. So when I have 100 data sets, I'm going to compute the prediction of the models trained on all the 100 data sets and take an average. Okay, that is the average prediction error. So the bias square is given by 1 over n summation I is equal to 1 to n h bar of xn minus expected value of y of n given x of n the whole square. So this I can compute this expectation because I created the data, like I know the sine curve like that is creating the data. And the variance is given by 1 over n summation I is equal to 1 to capital N 1 over L summation I is equal to 1 to capital L h L of xn minus h bar of xn the whole square. Okay, so we can actually compute all these three terms for this particular problem. And when I compute these things, it looks like this. Okay, so you see here that, okay, when you increase the value of lambda, so this is the opposite of our previous cartoon figure. Okay, so here in the x-axis, when you go towards the right, the model actually becomes less and less complex, right? So with larger value of lambda, the model is less complex. Okay, so it's a reverse. So the bias goes like this. Okay, so you see that, so this actually means the model becomes less complex. Okay, if you go this way, it means the model becomes more complex. As you can see, as the model becomes more complex, the bias decreases, the variance increases, right? And the bias square plus variance, there's a trade-off. Like, so there's a sweet spot where the error, the overall error is lower. Okay, and that also matches the test error. Is that clear? So typically, as the complexity increases, this is the complexity, okay? As the complexity increases, your empirical risk is going to keep going down. At some point, it's going to be zero. Okay, this is my empirical risk. So the training error will always go down as the complexity increases. Okay. However, the true risk is going to start increasing at some point. This is my true risk. Okay. And this is the ideal complexity. And anything that is below, like to the left of this, your model is underfitting. Anything that is after this, your model is overfitting. Is that clear? So there is a transition point where the model starts overfitting instead of underfitting. Like you need to stop there if you're looking for an ideal model. Is that clear? Any question so far? Okay, so we will stop our discussion on the decision theory and empirical risk minimization here. Okay. So today's class is the best example of a lecture that you should go back and watch the recording. So we are talking about a lot of things at an abstract level and more philosophical. And I think these are really important foundations that you should internalize. Okay. So the only way to internalize this is to watch the recording a few times. Like go back, listen to the recording for 10 minutes, like think about it, continue doing the same process. Okay. Okay. So now we spent a lot of time in this course on regression. We're going to switch gears and start talking about classification. Okay. And I think for the rest of the course, we will mostly do classification. We will come back to regression towards the end to see more advanced things. But for the rest of the course, we are going to focus on classification. Okay. Now, to have a quick recap, in regression, typically Y belongs to R, right? In classification, your Y belongs to a set of classes, right? The simplest form of classification is when y is either 0 or 1 or just yes or no. So we call these binary classification problems. Is that clear? Okay, let's start with an example. So here I have a bunch of yellow and blue circles, right? So there are two classes here. It doesn't matter what yellow means or what blue means. Like, so there is an yellow class and a blue class. Okay. Now, I'm interested in predicting the class for new examples, right? So let's say somebody gave me this particular example. So what do you think would be the class for this example? Or if you want me to be more clear, so this is the example we are talking about, right? So what do you think would be the class for this particular example? Yeah,
Yellow.
yellow.
With the yellow. With the same class as the yellow.
Okay, so let's do the reasoning later. So this is yellow. Okay, and what about this data point?
Purple.
Purple or blue? So okay, let's just call it blue. And what about this data point? So it's, well, we are not talking about algorithms here. Like, so it's just your guess, right? Like, so what do you think would this circle be? Yellow. So some of you say yellow. Like, does anyone think this is blue? It could be. So we are not very confident here, right? Like, so let's just say we are not confident. So why is it that we were so confident that this is definitely blue, that's definitely yellow? So what is your assumption here? You're making some assumption, right? Like, so what was your assumption? Yeah.
Looking at the nearest neighbors.
So you are making the nearest neighbor assumption, okay? Who knows? Maybe in reality, this is a blue, right? It could have been a blue, right? Like, so like we don't know the true data generating process, right? However, you are making this assumption, which is the nearest neighbor assumption, and you think that if everyone that is nearest to this data point is yellow, then it has to be yellow. Similarly, if everyone that is closest to this data point is blue, then it is blue, which is why your assumption kind of makes you stuck here. Like, so like you see that there are approximately similar number of blue and yellow data points. So it's not very clear like whether I should call this blue or yellow. Well, you can just try your luck and say this is blue, right? Like and like see whether this is blue or yellow, right? So we are making the nearest neighbor assumption here. Like I'm not gonna talk about how to do nearest neighbor here. Well, maybe I will write the equation still, but like this is very clear. Clearly, this is similar to what we did in regression, right? Like so, you find the most closest, like let's say top k neighbors. Instead of taking an average, you're going to do a majority of the class. Is that clear? Okay, so we can also do models like linear model for classification. Okay, so to do linear model for classification, first we need to change our classes to some numbers, right? Like we cannot do a mathematical model with blue and yellow color, right? Like so what we will typically do is we will either make this assumption that blue is 0 and orange is 1. In binary classification problem, you can consider the classes to be 0 and 1, or you could consider the classes to be +1 and -1. Is that clear? So both works. Okay, you can make either of these assumptions. And first, we're going to do a linear model. A linear model is given by y is equal to w transpose x, right? I'm going to fit a line okay, and say that in the case of 0, 1 classification, I'm going to say that, oh, my y hat is going to be 1 if y is greater than 0.5, and it's going to be 0 if y is less than or equal to 0.5. Okay. Similarly, when I have +1 -1 classification, I can say my y hat is equal to 1 if y hat is greater than okay. Just to have different terminologies, I'm going to make this y dash. Okay. It's going to be -1 if y dash is less than or equal to 0. So this is a lazy way of doing classification. Okay, so I already know how to do linear regression, right? So I'm just converting classification problem into a regression problem, right? Like what did I do? Like I made the targets to be 0 or 1 or +1 or -1. Now this is a regression problem, right? Like I can just fit a linear model to this regression problem. Now we don't care about the output of the regression. We actually care about the class, right? So to do that, I'm going to start making these rules. I'm going to say, oh, if my regression output is greater than 0.5, then I'm going to call it class 1. If it is less than 0.5, I'm going to class it class 0. Okay. And here I picked 0 as the threshold. Couple of questions here. First, why did I pick 0.5 and 1? So why 0.5 is the threshold when I'm doing a classification between 0 and 1? Yeah.
What's the number in between them?
Well, there is also 0.6, which is in between them.
Right, but it doesn't have any more bias for one-sided view.
Yeah, so without knowing anything about 1 and 0, like without knowing anything about the classes, you should go for the safest choice, which is exactly in the middle, right? However, if I tell you something about blue and orange, like saying, oh, like, so this is more likely or this is more likely, right? So then you can start tweaking. So this is, by the way, kind of a hyperparameter, okay, this threshold. Like, so like I chose 0.5, but it need not be 0.5, okay? So it could be 0.7, could be 0.6, right? The same is true for here as well. Like, so when you have a +1 -1 classification, when you don't know anything about the classes, it's safe to assume that 0 is the midpoint. Like anything above 0 is class 1. Anything below 0 is class -1. Okay. So this threshold, right? Like we're going to call this the decision boundary. Okay. So when my W transpose X is exactly equal to 0.5, that is my decision boundary. Okay. That's a line, right? Like W transpose X is equal to 0.5 is a line. I draw this line. Anything that is above the line is class 1. Anything that is below the line is class 0. Similarly, the decision boundary for +1 -1 case is W transpose X is equal to 0. Is that clear? Okay. So let's see how this looks like. Right? So in this case, I'm training a model y hat, which is W1x1 plus W2x2. There is no bias. Okay. There is no bias. And when I train a linear model and plot this line W transpose X is equal to 0.5, right? So this is the line that I get. Okay. As you can see, the line is actually passing through 0 because there is no bias. Okay, not a good choice, right? Like we should have a bias. For now, there is no bias. And anything that is above the line is orange. Anything that is below the line is blue. Is that clear? So is this a good model for this particular problem? No, there is a lot of misclassifications, right? So the simplest fix that we could do is to actually have the bias also so that my line can change a bit and come to the middle of this problem, right? Like so that is what I have done here. So this example, like my y hat is w1 x1 plus w2 x2 plus w3 or w0 if you want to call it. Okay. So when I draw the y hat for given x1 and x2, the line actually looks like this. Anything that is above the line is orange, anything that is below is blue. And this looks a little bit better. Right? Any questions so far? Okay, so I did not introduce a new algorithm today for classification. Like we're just reusing the linear regression, but as a classification algorithm. Okay, it's not a good idea. We will see why in the next class. Okay, but for now this works. Okay, and this is also something that we will repeatedly do in this class. Like so, we will every time we have a new problem, like we will try to reuse the existing solutions. If the existing solutions work, like keep using it, right? Like so, we don't need to invent new things. But when they don't work, we will try to understand why they don't work and try to fix it. Okay. So in the similar spirit, let's also do k-nearest neighbor classifier. So we did linear model for classification. Now we're going to do KNN classifier, which is similar to the KNN regressor. Okay. So the KNN classification algorithm is y of x is given by 1 over k summation xi belongs to the neighborhood of x, y of I, right? And I'm going to say the output is class 1 if y hat of x is greater than 0.5, and it's going to be class 0 if y hat of x is less than or equal to 0.5. Is that clear? Any question? Okay. So how would this algorithm look like, right? So let's do k nearest neighbor for the same problem. Here I'm doing k is equal to 10. Okay. So when I do k is equal to 10 and compute the blue and orange for every data point. Okay, so here the way in which I'm constructing this decision boundary, if you want to implement this like yourself, is you have to consider every single point and compute the k-nearest neighbor value and mark that as blue color or orange color. Okay, so when you do this, you see that the k-nearest neighbor actually has non-linear decision boundary, right? The decision boundary is not linear. It actually has this non-linear boundary. And what is interesting is within the yellow region, there is actually another blue region, right? Similarly, within the blue region, there is another yellow region. These kind of complex boundaries you cannot get with linear model, right? Like linear model is just going to give you a line. Now, even if you do basis functions, you're going to get a single curve, right? Like you will not get this kind of complex regions with a linear regression model, right? So now I can go to extreme and see what happens when I do one nearest neighbor. Like I'm just looking at one nearest neighbor. Okay, so this is how the one nearest neighbor would look like. As you can see, as you get close to one nearest neighbor, the decision boundary is so complex. Because there's high variance here. Okay, so when you have only one neighbor, every time the neighbor changes, like you have a different color, right? So you have a very high variance here. The curve looks a bit messy. Is that clear? Any question? Yeah.
In this case, going one with new values.
Yes, it will. Like, so let's do that. So, well, so the moment you plot the colors, right, it's very easy to use this algorithm. Like, so for example, let's say I give you a new data point here. It's blue because it is in the blue region, right? So I give you a new data point here, it's yellow because it's in the yellow region, right? Like, so I give you something here. So now you can say that this is blue. Like previously we had a doubt whether this is blue or yellow, right? When you start making the assumption that, okay, I'm going to use one nearest neighbor, it is blue. that clear? Any question? Yeah?
How do we choose the right number of neighbors without overfitting?
That's a good question, but by now you have the answer for that. So how would you pick the number of neighbors without overfitting? Sorry? Sorry, what? Adjusting K by using what? By using a validation set, right? Like just do model selection. Like so try different values of K, do model selection using the validation error, right? So there is no other right way to directly pick a number. Yeah? Yeah. The problem is simple, right? Okay. One thing I wanted to say when we were talking about the curse of dimensionality, what I forgot to say, maybe that's a good note to finish this lecture, is it's also related to what you said just now, right? Like, so we will see a lot of 2D and 3D examples in the class simply because we cannot visualize 10D or 100D or million dimensions, okay? But be careful. Like, don't generalize from the 2D example to a high dimensional example. Like, so interestingly, a lot of our intuitions break in high dimensions, okay? So the best example for this is if you try to imagine the distance between number 10 and 20 by closing your eyes, like you'll have some distance in mind. You can try to do this for 10 to 100, okay? But if you try to do this for 10, the distance between 10 power 20 and 10 power 21, it's not going to be proportional at all, right? Like so at high dimensions, a lot of these intuitions break. So you should remember that. Like so the trick is to understand things in low dimensions with a caveat that things could break in high dimensions, okay? However, this is not a big caveat simply because of my reasoning with images, right? Like so, even though it looks like we are dealing with a lot of high dimensional problems, they are inherently low dimensional. So most of these things generalize, but not always. So just keep that in mind. Like so like again, like I will do these simple examples in the class, but in your assignments, you're going to do like more features, like well, still not too many features. Like we try to make sure that the assignments are simple enough that you can run with Colab, like or with your local computer, right? Like so, like not something that requires big CPU or GPU, right? Like so, but still they are complex enough that they're more realistic than what we are seeing in the class. Is that clear? Okay, so I think we will stop here. Like I wanted to also finish the decision theory for classification, but it will be too rushed. So we will stop here and continue the discussion on classification in the next one. Thank you.